The afternoon session is from Mark Wolfman talking about probing the hidden world of battery chemistry using X-rays. So we'll talk for about 25 minutes and then we'll do some questions.
All right, great, thank you. So I'm a beamline scientist at the Advanced Photon Source at Argonne National Lab. So what that means is we have a synchrotron that is a 1 kilometer circumference electron ring. These electrons are going very fast, and as they bend around the corners of the ring, they give off these high-intensity X-rays. And these X-rays are useful to us for doing various characterization experiments. They have a few nice properties. One is the wavelength is on the order of what you would get with the kind of spacing of atoms within condensed matter, so that's really useful. And also the energy of those X-ray photons is enough to interact with the core electrons around the atoms. The synchrotron is necessary for a lot of this research because, one, the high intensity, and the second that's going to be relevant for this talk is we can change the wavelength of X-rays that we get at the sample by inserting a monochromator, and we can have very precise control over the X-ray wavelength. So we're going to put those things all together to do some studies on the dynamics of battery materials using synchrotron X-rays. These are the notable Python ecosystem packages that I used in doing this work. The ones on the left are fairly kind of ubiquitous for various sciencey things. The ones on the right are a little more specific to what I was doing here, so scikit-image and scikit-learn. TomoPy is for tomography reconstructions, PoreSpy for looking at pore networks and how they're connected, and then LMFit for fitting curves to spectral data. Everything that I've done here, or most of what I've done here, I have put into a GitHub repository. As a package, it's probably not particularly useful unless you're doing this specific application, but it is there for reference and if anyone is interested. Motivating a little bit why we care about any of this. So we all have batteries in everything we own now, cell phones, laptops, etc. An area, though, that is a little less visible is the effect that it can have on our electric grid. So typically over the course of a day, at night, there's not a lot of demand for energy. People are asleep. And in the late afternoon, early evening, there's a lot of demand because people are coming home, turning on air conditioners, things like that. Without storage as part of the grid, you need to generate all of this electricity on demand all the time. That can be very expensive, and if you fail, it can cause some pretty big disruptions to our industry and things like that. With energy storage, though, you can store the energy that's generated at night, and you can then reuse it when demand is high. So a little bit about how batteries work. So there's typically 2 electrodes. There's the positive electrode and the negative electrode. On the positive side, as you charge the battery, you are forcing electrons to move through an external circuit. When you do that, there has to be some other charge carrier that goes to the other side of the battery internally to compensate. And this is typically, for a lithium-ion battery, this would be lithium ions. That's where the name comes from. The main redox chemistry that's happening, though, is in the transition metal that is part of the cathode material. So in this case, nickel is going from nickel 3 to nickel 4, and that's really where the energy is being stored, is in the change in that redox potential. On the other side of the battery, you're going to have a similar process where the charge carrier is going to combine with the electron, and you're going to form a reduced species on the negative electrode. When you do this in discharge, everything happens in reverse. The relevant kind of things that we care about for the battery, one is the voltage, which that is a measure of how much energy is used or consumed for each mole of charge carriers that you move from one side of the battery to the other. So you want this to be as high as possible so that you can get as much energy stored in your battery as possible, though if it goes too high, bad things start to happen. And then capacity, that's how much lithium or electron charge we can move for example, the whole battery, or if you're looking at the material, maybe per gram of material, those types of things. This makes a nice picture, but unfortunately, real batteries often don't follow these nice pathways that we set up. We're kind of fighting thermodynamics because we're trying to store energy in a way where it wants to reach equilibrium, but we're not letting it on purpose, and we're trying to kind of guide it down one pathway. But that's usually not the only thing that's happening. So a lot of this research is in what are the other reactions that are happening, where are they happening, how are they happening, with the motivation being then that this will lead to designs for better batteries that alleviate some of these problems. In order to do that, we need to understand batteries a little bit better. So they tend to form a hierarchical system where at the smallest scales you have individual grains of materials in the positive electrode. These tend to be about 100 nanometers in length. So if you stack up 1,000 of these, you're looking at about the width of a human hair. Those form these 10 micrometer secondary particles, which you can see on the left. And then those form a composite electrode with carbon and binder. And that's what the final form of the battery cathode typically is. So I'm going to look at a few different length scales here. First, we'll talk about those primary particles, the 100 nanometer particles. Then we will start looking at larger length scales at the micron length scale. I will look at those secondary particles kind of in a dynamic experiment. And I'm also going to do a little bit of tomography of some battery materials where you can actually look at these things in 3 dimensions. First, we're doing tachography. This is a technique where you're taking a sample, which you can see here on the left. You put that in the X-ray beam, a focus beam that scans across the sample, and it produces this complicated interference pattern on the detector. You can then do some fancy algorithms to get back an image of the original sample with high spatial resolution. This is a pretty interesting topic on itself. If you were in Sahir's talk the other day, you got a good overview of how that works. But what we're going to do is we're just using this as an imaging technique, basically, and we're going to collect multiple images at ever-increasing X-ray energies. So when I say energy here, I mean like the reciprocal of the wavelength, so short wavelengths, high photon energy. And then we want to take these then 3-dimensional data sets where we have X and Y coordinates and then energy, and we want to reduce those into some sort of chemical map that will give us some insight into what the system is doing. In order to do this, there's a couple of steps, some pre-processing stuff we have to do first. So we're starting with an array that is energy and then row and column. So first we need to do a flat field correction. That's basically this equation down here on the left, where you're comparing the intensity at each pixel to what it would be if the sample wasn't there. This is pretty straightforward NumPy calculation. The next one is alignment. So since we're at the scale of like nanometers here, even just the thermal expansion from day to night will make the sample move in the beam. And so we need a way to make all of the images line up so that when we look at one pixel, we're actually looking at the same pixel across all the images. So to do this, we start by taking the median of our image stack, but only along the energy direction. And so then we get an image that's kind of an average of all of the frames. It's very blurry because of this motion blur, but that forms our reference image that goes into Scikit Image's phase correlation algorithm. And this will take a reference image and your target image, and it will tell you how much of a translation you need to line them on top of each other. So we do this for each frame. Do this for each frame, and that gets us a pretty good first pass alignment. We'll do this multiple times, and you can see here on the chart on the right, after we get to about 5 passes, we're not getting much more improvement on this alignment. So at that point, that's where we've typically stopped, though in some experiments we can go for a little bit farther. And then the last one is segmentation. There's some signal extraction stuff that I'm going to go over in the next few slides, but that works way better if the input to that is only actual pixels that have spectra in them. The background is mostly just noise, and that kind of confounds those algorithms a little bit. So to do this, we now take the average over the the X and Y dimensions so that we just get an overall spectrum for the entire particle. That's the mean spectrum here. And then the dot product of this with the entire 3D stack gives us a new image where the value at each pixel is the amount of spectrum that is in that pixel. So this is a good candidate for doing something like Otsu's threshold in scikit image, and then we can actually segment out what is particle versus what is background. So that's where we get something like this at the right here, where you can see the background pixels are just ignored. Okay, so in terms of results, so we took 3 samples. One we just had in the pristine state. Nominally, this should be nickel 3. The second sample we charged up to 4 volts. And then a third sample we charged all the way to 4.75 volts, where it should nominally be entirely nickel 4. Then taking the average spectrum over the entire frame, so this is all the pixels averaged together, now just looking at the energy spectrum, we can see that in the pristine, we have 2 peaks that are roughly equal in intensity. These are coming from the different interactions between the photons with the electrons around the nickel atom. So as the chemical environment around the nickel changes, we'll see those changes reflected in these spectra. And in fact, as we go to higher voltages, we see this right peak grow in intensity, and eventually it actually starts to shift over to the right. 4.75 volts is higher than you would typically run most batteries. Part of the reason for that is that if you charge it to that high, you very quickly lose capacity. So after a few dozen cycles, your battery doesn't really hold a good charge anymore. So manufacturers tend to limit these upper voltages, but if we can understand why we lose that capacity, that may be helpful. But what we really want to be able to get to is maps of nickel states somehow. So that's the next step here. This is building a little bit on Anna's presentation from this morning, but if we take this set of spectra now, we want to get out some sort of signal that is meaningful to us. So we can kind of model this as if we had a set of signals. So if we had n number of signals, and each one is associated, has a series of energies. And then we have a set of maps that produce one map for each of those signals and then shows you the map for how much of that signal contributes at that point. And then, to put it back together, you would do a matrix multiplication to get back your original set of observations. So the starting point was using scikit-learn's principal components analysis. This gives you kind of a quick way to evaluate how much information there is in some number of signals. So as you start doing PCA with more and more components, you start to notice that additional components don't really add additional information. They're just showing you kind of small variations on what earlier components were. So by doing this, we came to n equals 3 as a good number of components for what we're trying to do here. But again, from this morning's talk, non-negative matrix factorization is a much better way to do this for spectroscopy, in part because it's non-negative, and negative numbers for spectroscopy don't really mean anything. And then we added some additional information through a Bayesian analysis that a collaborator of ours did that also included some spatial and chemical information to try and get an even more physically meaningful set of results. So these were the signals we extracted. So for n equals 3, we get these 3 signals. We've kind of categorized them as reduced, intermediate, and oxidized. We're using these as proxies for those nickel oxidation states. We're not directly measuring those states because we couldn't isolate reference samples with those oxidation states, but this is our interpretation. And then comparing those to the observed signals, we can see that there's a good deal of overlap here where the reduced and the intermediate signals combine to give us that first pristine sample. And then as we get to more and more oxidized, as we go to higher voltages, we're getting more and more of the oxidized signal getting worked in there. And then we can use this to then get our maps, which is what we see on the right. So this is those three different particles, and these are the maps for each of those three signals kind of laid out on this table here. In the pristine state, which is the one on the left, you can see that the reduced and the intermediate and even the oxidized signal to an extent are more or less uniformly distributed around the particle, and this is what we'd expect. As we start charging, most of the oxidation is happening more towards the center of the particle. And when we get to the fully charged 4.75 volt sample, we can actually see a good deal of heterogeneity now in the particle. And the part that really stuck out to us is that there's still around the outside of the particle, there's a region of reduced material that isn't accounted for in the intermediate or oxidized states. And this actually is this is reduced nickel even beyond the starting point. So this is actually a nickel 2 species that we think forms when oxygen escapes from that crystal structure and you actually form a rock salt nickel oxide at the surface that's no longer reactive. So this may be an indication of what's happening in those batteries where you get to a high state of charge and you quickly lose capacity because we're forming these irreversible species at the surface. So the next section we're going to go to higher energy X-rays, so shorter wavelengths. These can penetrate farther into the sample, which is useful for us. Because we're using a different technique now, we can also do this by collecting the entire image all at once. So this can be really useful for doing some of these experiments faster. This gives us not as great spatial resolution. We're now at about 35 nanometer resolution. But because we're looking at those bigger 10 micron particles, we can, that resolution is plenty. So before we get into the kind of operando experiments, there's another set we did here where we're looking at three-dimensional imaging. This is equivalent to a CT scan where you take your sample, and for us, it's easy to rotate the sample. If you're getting a CT scan, they typically rotate the X-rays. But you go from knowing what the image is in X and Y coordinates to knowing what it is in horizontal and angle coordinates. So this phantom that's on the left here becomes this sinogram on the right. This is not useful for us, but this is the data we collect, and then there's a set of algorithms you can run that will reconstruct the volume based on those sinograms. The library that does this, one of many, but the one that we used is called TomoPy. This was written by Doga Gorsoy and collaborators at Argonne. And it basically is a set of tools that does that inverse reconstruction. One thing that they also developed, which I quite like, is this TomoPy CLI library, where every time you run a reconstruction from the command line, you give it parameters as arguments, and it generates a YAML file with all of the parameters it used, including the defaults and everything. And then when you rerun that reconstruction, instead of giving all the parameters, you can just give it that YAML file, and it will rerun the exact same reconstruction. You can also use that YAML file for other reconstructions and do it in a more self-documenting way. So we did this with some lead-acid battery electrode material. Lead-acid batteries are receiving some renewed attention, especially for some of these grid storage applications where you don't care so much about weight, you care more about cost and safety. So we were looking at some of these lead-acid battery electrodes, and you can see from these reconstructed images that there's a good deal of structure inside the electrode that has a big impact on how the material is going to behave. In order to analyze that a little bit more, we use this PoreSpy package, which will do network analysis on segmented data like this. And it will, one thing that is particularly useful is it will give you, so this is one slice from that segment, but the color here is telling you how small of a particle would you need to be able to make it to that point from the edge of the region. So, you know, even if the the main void is huge. If there's only a little tiny opening, that's actually the part that is limiting, is the size of that opening to get to that region. And then we can do some, make a histogram here of what the various sizes are that you would need to be. And then this will go into modeling work that will look at the transport of the electrolyte through the structure of the electrode material. And then the final section here is looking at doing these experiments in real time, where now because we're using harder X-rays, higher energy X-rays, we can actually look all the way through the battery stack while the battery is running. We had to cut some holes in the steel parts. X-rays at these energies still don't go through steel super well, but they go through everything else. And so as we charge, you can see here the charging profile on the bottom left. At each of these points in time, we collect one of these full frame sets. And so we can track the same particles over time and see how they're changing while we're charging. Doing those analysis steps again, we now have a 4-dimensional data set, so it's considerably bigger. Starting with the first step is to just actually reshape this so that it's really 3 dimensions, and you just kind of stack voltage and energy next to each other. But this data set didn't fit into memory, so we relied on SciPy. And then the other additional step is SciKit will give you the actual transform rather than just the values for the transform. And so what we would do is, so this is the kind of a condensed version of the routine I used, but for each pass here, the first thing is it will get the data set and apply any existing stage translations. Then it will do the registration using SciKit Images tools. And then it will stage those new translations along with all the previous ones. And it'll do this, five times, for example, as the default. Then at the end, we'll come back and we'll do a final pass where we actually apply the translations all at once. This minimizes the kind of compounding of errors you get, where every time you're interpolating these images with new translations, this way we just do it all at once and we kind of minimize those compounding errors. The other difference is that the spectra now look different. So because we're at higher energies, we have different physics that's kind of driving how these spectra are generated. But instead of individual peaks, we now have a big step here. And then there's what we call the white line at the top. This is the maximum intensity of the spectrum. It's called a white line because it used to be done on photographic film, and there would literally just be a bright white line where this maximum position is here. We can use the energy of this maximum here as a proxy for oxidation. So as the nickel oxidizes, the energy of this maximum moves to the right. We could do this with just NumPy argmax. But there's a little bit of a better choice here in that we can actually fit this with a couple of different curves. But the important one is the Gaussian curve here that gives us the position of this peak. This lets us be a little more precise than the 1 electron volt step that we use to actually collect the data. If you want to get really fancy, you could use X-ray Larch, which actually is meant for processing these types of spectra, but that was overkill in this case. So here's an example of some of those particles. We can see that they're oxidizing. This is the electrochemistry as the voltage goes up. The position of that white line also goes up, but you'll notice it doesn't go up smoothly the way we would kind of expect. So there's some steps in here to isolate the individual particles. Most of this is SciKit image stuff, but basically it looks at the distance from the edge of the foreground, and then it can kind of fill that in and it can determine which particle is which. And so if we isolate the individual particles, we see here that each one doesn't really react very much. So this is time along the bottom here, and then the change in white line position. So at the beginning, very few of these particles are oxidizing. And then all of a sudden, one will oxidize when something about the local environment changes. Based on some work with some physics modeling people using COMSOL, we figured out that the best explanation for this is actually the process by which the lithium atoms leave the surface and actually enter the electrolyte. So moving forward, I think our next generation of synchrotrons are getting ever brighter and generating ever more data. I think getting on top of managing this data and getting the electrochemistry and the X-ray data together and kind of all merged, I think that's going to be a big challenge. And so I'm really excited to see a lot of the things here, like the tiled API, ZAR, X-array, kind of all of these tools for managing some of that data. Here's some funding agencies and collaborators that I absolutely have to acknowledge. This is not all my work, so yeah. There we go.
All right, thank you. We have a few questions, although others, please feel free to throw them in. We have time. So first, both of them are actually kind of on something you presented earlier on
Yep.
the sort of spectral analysis and PCA and NMF. So could you elaborate again, or maybe restate, how that's being used? You're doing this, the NMF sort of breakdown of the spectral, the information. So how's that actually being used?
Right. So the PCA was really there just to figure out how many components we have. The results we get are not really all that meaningful from a physics standpoint. So what we're doing is we're trying to figure out. We're trying to get this here. We're trying to get an array that is the number of energy points and then signals for each energy point. So this would be like those three spectra. So like these three here, this would be that signals array. And so if you put the entire data set, so energy, row, and column, into the non-negative matrix factorization, it produces a set of signals and maps that kind of meet this criteria. So we're using non-negative matrix factorization to figure out what these signals here are on the bottom that we can extract from the data. And then we're using those signals to then figure out how much of each of those signals contributes to each pixel to make these maps here. So the maps are kind of the maps are kind of the goal for what we should get out of that non-negative matrix factorization.
Let's see. So then I think you sort of answered this maybe, but just to confirm, that the three that came from the PCA, is that informs the number of signals that's being used in the NMF? That's
right,
what you stated,
yeah. Yeah, so you need to tell NMF how many signals to give you. Right. The PCA was, so if you just kind of do it blindly, you get a lot of signals, but most of them don't mean anything. And with PCA, we could look at, let's say we did 3, and we got 3 signals that are distinct. They're not physically meaningful, but they're distinct from one another. And then if we do it with 4, the 4th one was actually the same as the 3rd one, but a little bit tweaked. So it wasn't really a new source of information. It was just a kind of correction of one of the other signals. And so that's why we stopped at 3.
All right, so we have a question. Did you or are you planning to work with solid-state batteries as well?
I have worked with solid-state batteries. We've worked a little bit on the electrolyte. So solid-state batteries have a couple of different, kind of very different chemistries. The one we've worked at is lithium lanthanum zirconate, LLZO. The one that makes this one a little tricky is that lanthanum is very absorbing. And so you're kind of trying to look through like a lead shield for like a piece of paper on the backside, right? The contrast is just not there. But yes, we've done that. We're more interested in what is the structure of the morphology of the solid electrolyte, because that can have a lot of impacts on it.
All right, and we have maybe two final questions. So, do you have a protocol for masking non-sample components in the operando setup?
Yes. So that actually, there's 2 steps. One is we moved to a region where there's just no particles. We collected a flat field image and then we move back to where the particles are, and then you just divide those out, and all the things that are coming from like the window or the lithium, that type of stuff, goes away. The other thing we did is because for the operando cell we have this big jump here, we actually just split it into two sets. That is, what is the intensity above that jump and what is the intensity below that jump? And then I put that into Otsu's thresholding to sort out what is foreground and what is background, just based on what we call this the edge jump. What is the edge jump? And that scales with how much material is there. So in regions where there's lots of nickel, this will be high. In regions without nickel, this will be almost zero.
All right, last question is, do these techniques, or does this analysis work well for interfacial regions and possible interface formation, like a cathode electrolyte interface?
For the CEI? It can. The trouble with a lot of those layers is they tend to be made of really light things. So what they're asking about is there's a new phase that often forms between the electrolyte and the electrode material, but it tends to form from a combination of lithium and carbonates and things like that from the electrolyte. And so it's hard for us to see because low Z elements are almost transparent to X-rays. So, but in theory, yes. It depends on what it's made out of.
Sure.
What about the concern about electrolyte penetration? Is there a way that one could verify that we do get good electrolyte penetration to the whole particle?
Yeah. Are you asking about like the lithium-ion particles or the lead-acid one where we did or either one?
Electrolyte carrier itself.
Yeah.
Sometimes, porous media, you don't get electrolyte all the way into the substrate.
Yes. So in the case of our in situ experiments, because we're making dilute electrodes on purpose, we actually kind of are making it easy for the electrolyte to get there. So that actually, it's an interesting question because it could have something to do with why we're seeing this behavior here, right? Why are we seeing these particles oxidizing kind of quickly? So that could be part of what is causing the timing between different particles. It's really hard to see here, again, for very similar reasons that the electrolyte's made out of low Z elements, and so you just can't see it. We've tried, but everything we've come up with has run into one issue or another that typically comes from just the X-ray technique. But, yeah.
All right, let's thank our speaker again.